So now that we've mastered the basic components of electric circuits, namely potential difference, current, and resistance, and then also power, we're going to start putting it all together. We're going to apply our principles that you should already be familiar with, namely conservation of energy and conservation of charge. And we're going to apply it in the context of two rules, which we're going to call Kirchhoff's rules. Here is a print from M.C. Escher from 1961. I like these Escher drawings because they kind of show us that we have an intuitive understanding of physics sometimes, even if you don't realize it. I mean, looking at this, you see the water going down the channel, and then eventually it goes over a waterfall, and that waterfall will then run a water wheel, and then the water will go down the channel some more, and it ends up going back and being on the waterfall again. We know that can't happen. We have an intuitive understanding that certain things you get out of it what you put into it. And that is our understanding of the conservation of energy. Here's another example of kind of the same thing. The question I ask here is if you have this water wheel, and the water wheel is being powered by water that has been pumped up to a high place by the pump, can I use the energy from the water wheel to not only run the pump to pump the water back up to run the water wheel, but can I also use some extra energy then coming out of this to work this device? We realize intuitively, I think, that this doesn't work because it's like you're getting something for nothing. Not only are you getting enough energy out of the water wheel to run the pump the water back up, but you're also getting extra energy out to run the device. We realize it doesn't work because we understand the law of conservation of energy. So we're going to apply the law of conservation of energy to circuits now. In a moment, I'm going to use an analogy with gravitational potential energy to show you how we're going to do that. Hello. We're here today to talk about circuits, but before we do that, I'd like to start talking about Hot Wheels cars, because we're going to use an analogy to what we learned about gravitational potential energy to learn about electrical potential energy. If you remember in the fall semester, we did do some experiments, like one we took a ball and tossed it in the air, and we said that once we put energy into the system, that energy stayed constant more or less if we could ignore any energy losses because of the air friction. In other words, the kinetic energy got converted into potential energy when the ball was going up and the force of gravity was pointing down. The force of gravity was doing negative work, and so the potential energy increased. When the ball started coming back down again, the kinetic energy increased and the potential energy decreased, but the total amount of increase in potential energy was equal to the decrease in potential energy once you return back to the same point. We can do that with a Hot Wheels car. Let me demonstrate. Bring a Hot Wheels car up here. I'm giving it some potential energy by doing work against the force of gravity. Now, I let my Hot Wheels car go down the track. It loses potential energy because gravity is doing positive work on it. Work is being done with the force of gravity, so that potential energy is lost. The amount of potential energy it gains in lifting up to a certain height is equal to the amount of potential energy that it loses, say gets converted to kinetic energy in this case, when it goes down to that same height it started at. Another way of saying the same thing is that the net change in potential energy, if you start at some position and you end at that same position, is zero. So for example, if I start with my car here, right here at this level, I bring my car up. It doesn't really matter what path I go on. I bring it up to this level. I've gained some potential energy. But if I let the cart go down the track and ends up over here, the loss in potential energy is equal to the gain in potential energy. So another way of saying it is that the net change in potential energy of my car when it returns to its starting position is zero. One thing I should clarify before we start talking about applying that to electric circuits is what happens to the energy that it loses. We're saying that the potential energy is taken away from my system when my car does, or when the gravity does positive work on my car. When I put it down this track, the potential energy just becomes kinetic energy. But in this back track here is probably a better analogy for what happens in a circuit. You see here, the energy is continuously taken away by these little bumps. We saw those bumps before. So I start there, and there, and there, and the cart kept slowing down by these little bumps, and it had to have some more energy to get it going again, and then it slowed down and got some more energy to get it going, and so forth. So in an electrical circuit, as we're going to see, the energy is continually taken away from the charges, and it's going to some other form, perhaps light or heat in the case of a resistor. We're going to see more about that once we understand what happens to potential energy in circuits. So we'll do that next. Okay, so now we're going to do the same thing with an electric circuit. And believe it or not, this is more or less what we just saw with the Hot Wheels cars. I have a battery here, 2 cells in a battery, and that battery does my work for me, literally. It actually does a chemical process which gives energy to the charges that flow through it. It gives them potential energy, just like when I raised up the Hot Wheels car. And then I have a wire here, and that's going from the positive side of the battery over through here, in through the light bulb, lighting it up, and then coming back here, and it goes back to the negative side of my battery. And what we're going to do today is we're going to measure the potential differences. That is the change in potential energy per coulomb of charge that flows from the black probe to the red probe. And I know you can't see these numbers over here, but I'm going to read them out to you as we do it. And you can see, we'll write them down and then we can analyze them later. Okay, so starting at the base of my battery, the negative side of my battery, and going to the positive side of my battery, I have a potential difference of 2.545. So 2.55. And I'm going to call that point there at the other side of my battery is point A, and the point of the positive side of my battery is point B. So that's 2.55 volts. I already have the diagram and everything ready for me in my lab book. That's a good idea for you to do. And now I'm actually going to measure the potential difference from this point in my circuit, where I just had the positive before, over here to the light bulb. And now it says a negative 15 millivolts. So that's point, I was actually point, let's see, there it is, 11.2. So negative 11.2 millivolts, I'm going to convert that to volts. That's 0.011 volts, and it's negative. Okay, and then I'm going to measure the potential difference across my battery. My light bulb. And I go from the side of my light bulb that is closest to the positive of my terminal. So I'm watching the charges as they go through my circuit. And it's a negative 2.52. Negative 2.524. So it's called negative 2.52. Negative 2.52 volts. And then lastly, I'm going to measure the potential difference across this wire here at the end. So we're going to go from here, where the other one was, back to here. And it's a negative 0.06, no, see, 6.3 millivolts, so that's 0.006 volts. Volts. Okay, and with that information, we're going to see what happened. We will write this up, and I'll show you what happens in the PowerPoint. So here are the results of our experiment, written up in my lab notebook, the way I expect you to kind of write things up. A couple of things to point out. When you are going across the battery from the negative side to the positive side, the potential difference is positive. The charges at the positive side of the battery, you've collected positive charge up there, and so they have a positive potential compared to the other side of the battery. That potential difference has a name. It's called the electromotive force, or EMF for short. We actually don't use the word electromotive force anymore much because it's misleading. It implies that it's a force, and it's not. It's a potential difference. So we'll just call it the EMF of the battery. The EMF is the potential that you get because of the chemical reaction in the battery itself, and it's abbreviated with the Greek letter epsilon. Another thing to point out is that the potential difference going across the resistor is negative. You're giving up that energy as you go across the resistor, and so you're going from a place where the charges have a high potential energy per unit charge, or high potential, to a place where they have a lower potential energy, so it's negative. And there are the numbers that we wrote in our experiment. So here is a graph showing those potential differences that we had in our experiment. I arbitrarily decided that point A was going to be my zero of potential. So, and I graphed potential differences. So going from A to B was a potential difference of a positive 2.55. And so going from 0 to 2.55, B is at 2.55. And then I graph from B to C. I'm going to have a negative 0.011 volts, and so I graph that potential difference as well. And going from C to D is a negative 2.52 volts, and then from D back to A is a negative 0.006 volts. Now what you'll notice about this graph is where I ended up. If you look at all those potential differences going from A back to A, it looks like I have pretty much ended up back where I started. In other words, at a zero potential difference from the, if I end up back at the same point, I have a zero total potential difference. And that's actually a general rule. If you start at any point in a circuit and end back at that same point, the sum of all the changes in potential should equal zero. This is a consequence of the fact that the electric force is a conservative force, and that expresses itself the idea of conservation of energy. This is known as Kirchhoff's loop rule, and it's one of the two powerful rules we're going to use to analyze circuits. Okay, so here is a practice using that Kirchhoff's loop rule that we just learned. It shows a battery that is connected to a resistor and another battery and another resistor. Now the resistors are identical, and just from the symmetry of the situation, we should be able to guess that they should have the same potential difference across them. So let's see if we can figure out what the potential difference across each of the batteries would be. Go ahead and pause the video now, and when you think you have an answer, start it up again. Okay, so looking at the circuit, we see that on the left side, if we were to start the lower left and go up, we would gain 9 volts in that battery, and then we would have some potential difference dropped across that resistor. And then you'll notice that we're going from the positive to the negative side of the battery. If you keep going in the circuit the way the charges would go, if we go from the positive side of the battery to the negative side of the battery, we're actually losing 3 volts. And then we would go through the potential difference again. So if you start with plus 9 volts, minus V, let's call it, minus 3 volts, minus V gets back to 0, that tells me that each of the resistors must take away 3 volts in order to get back to 0 when you get back to the starting point. The 2 resistors that you saw in the previous problem were arranged in what we call a series arrangement. In a series arrangement, there is only one path for the current to follow when going through the circuit. In a parallel arrangement, there is more than one path for the current to follow. And that has some consequences on how those circuits behave. We are going to do an experiment virtually with a series and a parallel arrangement of resistors. One of the things that we are going to be able to find using Kirchhoff's rules is going to be what is the equivalent resistance of the arrangement. These 2 sets of arrangements of resistors here, even if they were the same resistors, they would have a different effect on the total current flowing in my circuit with a given total potential difference. And so we call that the equivalent resistance. That is to say, it is the total potential difference of my circuit divided by the total current flowing into my circuit. So ideally, we would have done this resistor discovery lab in our laboratory, but we can do it online just as well. What this involves is setting up a series circuit with a 10 ohm resistor and a 50 ohm resistor, and then measuring the voltage drop across each resistor, and the current in each resistor, and the total voltage and current in the circuit, and determine the equivalent resistance. And then doing the same for the parallel circuit with the same 2 resistors, but now put them in parallel and measure the voltage drop across each resistor and the current in each resistor's branch, and then the total circuit voltage and current. And also determine the equivalent resistance. So you would divide the total voltage of the circuit by the total current flowing in the circuit. Okay, so I'm going to give you a place to stop this video now and go to our circuit simulation site and do the virtual lab. When you're finished with that, you can come on back and watch section 2 of this video.